So I'm Larry from Google. I came here today to talk about LinuxBoot. So LinuxBoot is, the aim of LinuxBoot is to replace large portions of proprietary firmware with a Linux kernel. So this project isn't from like a single team or a single company. It's a large collaboration between many people, as you see here. So I'll begin the talk by talking about the existing UEFI booting system. So I'll give an overview of it and how we'll fit LinuxBoot into it. Following that, I'll discuss how you can take your own firmware image, extract the pieces from it, and replace the necessary components to use Linux as firmware. Then I'll talk about the init ramfs that we use at Google called uroot. Finally, I'll talk about future goals and the people involved in the project. So some of you may have already seen this image. So it's the phasing of UEFI. So it starts at security, PEI, then it runs drivers, then it selects which boot device to use, which essentially continues to boot grub, then Linux. So UEFI has many OS-like features. It has scheduling, it has events, it has a file system, applications, an entire network stack. It has drivers for disk, drivers for USB. And the general idea is, why do we want an operating system to run before an operating system? Like, why can't we go directly to Linux and use all the existing drivers that it has? So I'll talk about some good parts of UEFI and some issues that it has. So the good parts, it has well-defined phasing. It's definitely architecture independent. It's a lot more than the previous implementation, a lot more than PC BIOS. It's modular, replaceable, has its file system. You can replace individual files with other files. It has support for backwards compatibility, and definitely has a very, very wide adoption, especially among x86. It has pretty much any laptop, server, or x86 system will use UEFI. The issues that it has is a lot of the implementations, it doesn't have to be this way, but a lot of the implementations are closed source, so you cannot view the source code and know what you're running. It can be hard to update without vendor support. If you want to write drivers for it, you first have to learn you have to learn the UEFI libraries and how to implement it in a certain way. If you already have knowledge of writing Linux drivers, it doesn't transfer too easily to writing new UEFI drivers. And there's a lot of legacy code. Okay. So what we want to do is we want to end at the Dixie phase. The drivers, we want to remove some of those drivers from that phase as much as we can, and replace those drivers with drivers that are found in Linux. So the Dixie core, at the current moment, we have to keep the Dixie core because it sets up some ACP tables and other driver initialization. But in the future, we plan to drive it back all the way to PEI. So how do we do this? How do we get from here with all of Dixie phase and all of boot services to here? How do we place it with Linux? So there's five steps you have to follow to do this. So first, you have to get your existing firmware image from somewhere. Then you can list all the Dixies, all the drivers that it contains. Then you remove as many drivers that you can that are made redundant by Linux. For example, you can remove the USB drivers, the network stack. Then you add Linux to the firmware, like inside the flash pot, as an EFI application. And then finally, any remaining Dixies, you could attempt to replace them with open source drivers that you find in EDK2. So how many of you have seen or used one of these? All of your hands up. So if you crack open your desktop, you'll find a flash part, and these are the tools you need to read off the firmware image. So you need a program or like a reader. You don't necessarily have to use a DediProg. There are many cheaper varieties. You'll need some sort of connector. A lot of motherboards might have headers. If not, you have to use one of these Pomona clips. And FlashROM is probably one of the best tools you can use to software to read the firmware image off. So these are some of the Dixies that we found in Winterfell. This is like a small selection of them. I think there's over 100. But you can see here, there's Dixies related to USB. There's some network stack Dixies. There's some old disk Dixies, the ISA bus. There are Dixies which are misspelled, thermometer. So a lot of these Dixies aren't audited. Like for security, network stack, you may not have access to the source code, so you don't know how secure it is. So our aim is to remove as many of these as possible. And it's kind of like removing blocks from a Jenga stack. If you remove the wrong Dixie, it will all collapse, all fall apart, the system will no longer boot. But when you remove the right drivers, the system will still boot, and then you could use the drivers that are available in Linux. A lot of these drivers are just easy to move. You just simply delete them, and they're gone. Some of them you need to do some careful massaging, some careful working around in the UEFI code to understand. So a comparison on Winterfell is we started with over 100 Dixies, and we reduced it to 31 files, which is a huge improvement. So the remainder of these are Dixies which load ACP, SMM, SMI. In the future, we want to try to remove these as well and push it all into the Linux kernel. But at the moment, that would require a bit of work. So to remove these drivers, that's where the tooling comes in. So we have to be able to extract a firmware image and view the files within it. So you can think of a firmware image as a sort of like a file system that you could sort of mount and view the files within. But there's a few tools that you can use to do that. So probably one of the easiest to use is LinuxBoot. Essentially, for LinuxBoot, you could clone it, you read your firmware image, you dump your firmware image into the correct directory, and you then make your board name, the kernel, the manifest you want to put into it, and you just run make. And that will update your firmware image by deleting unnecessary Dixies and inserting the kernel into it. So this only works on select boards, as listed here. And it requires, in the kernel, to have these configs set. So EFI stub makes it readable from UEFI. The EFI BDS means it can be used as it's a patch which allows it to be used as from the boot device selector. Another tool, which has a GUI interface, which is easy to use. It's not as automated, but it lets you list all the files, and you could select individual ones that you want to delete. So for example, if you wanted to delete that file that's selected there, you could just right-click, delete it. This tool has been around for quite some time. It's a bit inconvenient. It's great for playing around with, but if you want to have an automating system, you need a command line. And there's two command lines for this tool. There's UEFI replace and UEFI patch. So they let you access the firmware image from the command line and automate your process. If you check it out from this repository, make sure you check out the new engine branch. That contains a lot of new features which aren't on the master branch. Finally, one of the tooling that I've been working on quite recently is the UEFI toolkit. So it is a purely command line interface. It has different various commands for example, the table command, which lists it all out in a table, the GUIDs, the types, the sizes. There's a remove command for removing the specified file. You can combine commands inside of a pipeline. So for example, you could take the image, you first load it, you remove everything that contains USB, you can remove a Dixie by its GUID, you can replace the shell with your Linux kernel, and then you save it back out to another file. There's also other commands here. We have cat, which dumps the file to your file system, find, which outputs some JSON or metadata about a file, and it's fairly easy to add more commands to it, so it's about 80 lines of Golang. We're planning on writing some analyzers for UEFI. So once you delete the drivers which you don't need, and you've inserted the Linux kernel into the EFI image, it will. The next step is from your kernel, you want to kick, so the kernel, the boot kernel, runs inside, it's stored inside of the flash image. So from there, you want to find the runtime kernel, the one you'll be actually using on your machine. Like it will have all the applications, like it's the final destination, like the final kernel you'll be running. So the idea of the boot kernel is it would go fetch the final kernel from the network, or it could fetch it from the local disk, or it could fetch it from pretty much anywhere. It would then check to make sure the signature is correct, and then perform an operation, a kexec, which is essentially it switches from the current running kernel to another kernel, and it will essentially clear all the memory, or all information of where the previous kernel was. So what have we gained by doing this? Why have we performed LinuxBoot on the firmware? What benefits does it give us? So first we've removed all the duplicate drivers from the system, which has benefits in, for example, we don't have to care whether or not those drivers were closed sourced, which gives great security implications. Secondly, we no longer have to have Linux kernel engineers can now write drivers for the firmware. They no longer have to understand the UEFI stack and the interfaces it contains. Thirdly, there's a great improvement in speed. So for example, Winterfell, we noticed there's a huge improvement from 8 minutes to 20 seconds. Pretty much every platform we've installed or we've performed LinuxBoot to, we've seen at least a 10 times improvement in speed. So two common questions that come up in these talks is, are we simply replacing grub? No, we're replacing what runs grub. So grub typically runs, at least in UEFI, it runs as a boot device that the UEFI that runs after UEFI, but what we're replacing is UEFI itself. And then the second question that often comes up is why should Linux boot another Linux? Isn't that slow, or like why can't the first Linux be the final Linux on the system? And the primary issue is the flash size is so small that it wouldn't be able to fit all the drivers necessary. But you could do this if the flash part was large enough, or if you're booting from something that's not a flash part, which has sufficient size. You could run it in what we call kiosk mode, which means the firmware Linux is the final Linux. So this process doesn't only apply to UEFI. It can also be applied to core boot and U-boot. And it's also not a new idea. So it's probably over 20 years old. So LinuxBoot, what was before core boot, originally used this system. Opal uses this. Some ARM devices use it. It's fairly well known. So the question now is, we've inserted a Linux kernel, and it will kexec another kernel. But what do you use as the init ramfs in the boot kernel? And the answer is anything you want. We don't provide tools. We only provide, we provide tools, but not the policy. So you could use BusyBox, you could use systemd, you could use petit boot, you could write something on your own, you could use anything in the init that you want. For example, Tremel, he uses heads, which is a security-focused version of BusyBox. But the important thing that it has to do is whatever you implement has to provide all the correct drivers that you replace in UEFI, as well as the bootloaders. And if you need it, it should also provide a shell. So at Google and at ITRenew, they use uroot, which is a universal root written in Golang. So the big advantage of Go is it's architecture independent. You write Go code, you could easily, very easily compile it to ARM, to x86, to PowerPC. The toolchain is set up for that to do it extremely easily. You just set an environment variable. You don't have to download a separate compiler. It's much easier to use in C. And it is also incredibly small if you use the correct techniques. So for you, we set up we've set up many commands. At the current moment, we have 99 commands. Probably some of the most important ones are kexec, which executes the next kernel. We have PixieBoot, which is an implementation for the PixieBoot network booting protocol. We have wget, which, if you can, you should prefer to use wget over PixieBoot. We have GPGV, which signs keys. It checks that the signature is correct for a signed key. So everything is here, everything necessary is here for booting an image. We also have other firm-related commands, for example, cbmem, which is able to access core boot. So what other advantages does Go give us in firmware? So Go has a lot of built-in static analysis tools. For example, GoVet, GoLint, GoFormat, InFSign. So these help you find bugs in your source code. They're very easy to use. You can set them up to run automatically when you make a change. It has a built-in race detector and memory sanitizer. It's almost impossible to write a buffer overflow in Go. It will simply panic. You could catch the panic and recover. The documentation for Go is all open. If you go to the godoc.org website, it has documentation for every single project, which is on GitHub. The language is very type-safe, especially compared to shell scripts. One of our big aims is to no longer write shell scripts, but to write all of what we would have written as a shell script in Go. Additionally, the language has a huge library. For example, has a network stack. It has libraries for reading and writing to JSON. Pretty much anything that you need is supplied in the library, and the library itself is of high standard, and it is also very secure. And one final thing is it is very fast to compile. As you'll see in a bit, it can compile all of our source code in about 8 to 10 seconds, I believe. It depends on your system, of course, but it's very fast. So there's two ways we use reroute. The first one is source mode. So in this mode, we store all the source code. So we don't compile it on your development machine. We store all the source code in the firmware. And then when it runs, when you boot your machine, it will compile the source code on the fly and then run it. So in your init manifest, you would have 4 binaries. You'd have the Go compiler, assembler, and linker. Then you'd also have the Go command, which also acts as an init command. So this is very versatile. It means all the source code is in your firmware image, which makes it a lot easier to audit and understand if you ever have to open it up again. It's also very small, so we found that it's about, I guess depending on how many commands you include, we found it's about 4 to 8 megabytes. It's also architecture independent, except for those 4 commands. You could supply different commands for different architectures, but all the source code in the firmware image doesn't change between builds. The second mode, which is probably the more popular one, is a busybox mode. So in this mode, we compile it from on your development machine before we put it into the firmware. So this is the main advantage of this one over source mode is it is much smaller. It's about half the size. So the idea behind this, if you've heard of busybox before, the GNU busybox is a similar idea. We compile all the commands together into one binary, and when the binary gets executed, it will look at argv0, and depending on the value of argv0, it will multiplex to a certain main function. So for example, if you have the ls command and a cat command, you compile them together, and when you execute that binary, you set the argv0 to cat, and then it will execute the cat's main function, and you set the ls, and it will execute the ls's main function. And to set up argv0 conveniently, you use symbolic links. So the reason this is a lot smaller is because it shares a lot of the binary code between all the commands. So all the commands are in one binary. So there are a few implications of this. So PXE-boot in Golang, it's an isolated process. Unlike in UEFI, it's isolated. If there's a memory issue, it won't, for example, it won't have any access to other processes. It's a lot faster. As we saw previously, it's about 10 times faster boot speed. Reasons for this is the Linux kernel is preemptive. You could load multiple drivers at the same time. The Linux kernel has also been very well optimized for boot time. And congestion control, so the network access is often a lot faster. So to continue, we're going on to the people who are involved in U-Boot and LinuxBoot, as well as some philosophies behind the project. So as I mentioned, we have users from Facebook who are testing switches, servers, embedded systems. From IT Renew, we have Jean-Marie, who resells decommissioned servers from the Open Compute platform, and he's shipping with LinuxBoot. We also have some other experimental projects, for example, the Equus servers, the tie-in boards, and various system on chips. So some of the philosophies is, like mentioned earlier, is tools, not policy. So we develop lots of tools, but it's up to you exactly how you use these tools and which commands and how you write your own boot process. So security and user freedom. So it's both. Security features should allow change of ownership, reprovisioning hardware with your own keys. And finally, we have tools for boots, not bricks. Okay, so, something major that happened in January is we joined the Linux Foundation as one of the projects. So we have, I think, the 3 members of the steering committee are here today. So we have Ron Minnick, we have Jean-Marie, and Philip from 9 Elements. And lastly, our last user, or our last involvement is with the Open System Firmware Group. So we have weekly calls with this project where we are working with the engineers to incorporate LinuxBoot and OpenEDK into the Open Compute project. So this is some of the future for LinuxBoot. So one thing we're working on right now is getting a LinuxBoot book set up. So the idea behind this is anyone could contribute to the book. You could read it, and it will have all the documentation necessary on several different platforms. We're also looking into helping vendors support LinuxBoot. We want more hardware to ship with LinuxBoot rather than putting it on as afterthought. We are working on these two projects, like I mentioned earlier. SMM, possibly the idea is SMM-free, so we'd use no SMM mode for x86, as well as Dixie-free, where we completely remove all the drivers from EFI, and to create the ACP tables, which would require creating the ACP tables in the startup kernel. Finally, for URoot, we're trying to put it to a Bazel build system, incorporate the Bazel build system, as well as the Go modules build system. So here are some ways you can get involved. You could join the Slack channel. You could read our website. You could try URoot. That's a command that will, pretty much 2 lines, you get it set up on your machine. You could read, you could contribute to the book. We don't have many chapters at this point. And if you're interested in having, if you're interested in running LinuxBoot on your own hardware, get in contact with us or ask on the Slack channel, and we'd be more than happy to help. Okay, any questions? Yes, one.
I was not prepared for that.
Thanks a lot for the talk. It's definitely a very interesting project,
Yep.
and the idea to make use of Linux and all of its capabilities is definitely a good idea. I mean,
Yep.
just the fact that most network cards have a special PXE boot mode to basically reduce your 500 queues to only a single one to pull packets one-on-one from the network already tells you how ridiculous firmware is these days. The problem is, so I work for SUSE, and from a distribution point of view, from an OS point of view, what we really need is a single, not 500, a single way to boot. We want one interface, we don't want 5. We want one interface to work against. So what we standardized on these days, mostly on the x86 and ARM world, is UEFI. Which then again gets me back to the extra question, how far are you along with implementing UEFI boot time and runtime services inside of the LinuxBoot environment? So how far are you along with getting the payload you're running after LinuxBoot to actually just see something that would look like UEFI from the front?
I don't think we've had much progress with that. I believe IBM has been working, don't quote me on this, but I believe some people have been working to run EFI drivers within Linux. Also, I believe you could get the runtime kernel to believe it's being executed directly from EFI if you don't exit boot services inside of the boot kernel. So if you leave boot services enabled throughout the boot kernel, it should be possible to pass on boot services to the runtime kernel in which it could exit them there, and then it would have access to all of the EFI protocols and whatnot.
Any more questions? Oh.
Hi, I guess you may not care, but I'm absolutely astounded that it takes 20 minutes to boot any platform through the firmware. Can you, I did once see this on a UEFI platform. I had serial enabled and it outputted about 8 minutes worth of serial at the baud rate I was using. But apart from that, I can't understand it. Do you have any insight into what on earth is going on?
Oh, what on earth is going on? So this is mostly for servers. This really long extended boot time is mostly for servers, because if it was ever consumer hardware, no one would ever buy a laptop or desktop machine for themselves, which would take 20 minutes to boot. So this is mostly an issue on servers where you could people can sort of wait that long for the server to boot, but it's not fun. Mostly what it's doing is, first, UEFI is mostly non-preemptive. So for example, if you have multiple disk drives connected, typically it initializes each disk drive one at a time. It's difficult to initialize them all in parallel. Secondly, there are many issues with the dispatcher. So for example, it might try to reinitialize something that has been initialized before. It could jump back and forth between initializing different things because something depends on something else. But since it's already been initialized, it doesn't have to be initialized again, but it tries to initialize it again because it doesn't remember or for some reason. So the dispatcher behaves in strange ways sometimes, which leads to these very long boot times.
Any more questions? Over there. You're letting me get some work out here.
Thanks. This is Shubrata from Intel. I have a question regarding your removal of Dixie.
Yeah.
Why don't you use FSP? Is there any restriction there? Because what you want the platform code, like platform initialization, right? Eventually, because the removal of Dixie might need to deal with all your dependency. For example, you were showing the Pixie boot, right? The Pixie boot has around 10 to 15 module, like a recursive dependency and all. So just wondering, what's your plan to use the FSP?
I think the plan is not to use FSP. The plan is mostly to remove as many Dixies as possible, preferably until they're all gone. So we boot directly from, during the boot phase, we boot from the PEI phase directly to Linux. I believe this is for machines without an FSP.
The one thing I have heard from just one company that did have FSP servers is they were going to use core boot to go to LinuxBoot. And my talk this afternoon, I may touch on some of that because that's a core boot talk. So.
Thank you.
So, any more questions? Yeah.
Hi. What did you settle on now on the naming for the different kernels? So runtime and boot kernel or run kernel? So what's the
so I think
is the solution?
The official naming that we agreed on is the boot kernel and then the runtime kernel. But sometimes the boot kernel is also the runtime kernel because it doesn't kexec into another kernel. It's like the final kernel. In that case, we call it kiosk mode. So the naming could get a bit confusing. But mainly if you're doing a kexec, we have the boot kernel and then we have the runtime kernel. The naming sort of mimics EFI's naming of boot services and runtime services. So, yeah.
Are there any more questions? Yes, there are.
How small were you able to make your boot kernel, and do you publish your kconfig options for paring the Linux kernel down, because it has traditionally kept getting bigger and bigger and bigger?
Yep. So at least for x86, the easiest way to make a small kernel is you type make tinyconfig, and it will use the minimum number of make options as possible. And then we have published a list of the minimum config options you have to enable for Go to run. There's about 20 config options you have to enable. Things like the terminal, you have to enable some few texts and some other things. And that's published on the, if you go to github/uroot/uroot, it's in one of the README files there. How big does it get? You can make an x86 kernel as small as probably 900 kilobytes, but it has almost nothing inside of it. Which it's very small, but you won't have any networking. You may not even have like the block layer at all. So it does almost nothing, but it's very small. And then when you add networking, the block layer, like it gets up to around like 1 or probably 2 megabytes at that point.
Okay, any more questions? Yeah.
Hi, I'm wondering about the iSCSI boot scenario during the boot kernel phase. The customers we're having Dell HP are using the BIOS configuration menu for iSCSI configuration. Basically, I'm wondering how it's going to be solved in the boot kernel to pass through the data they're giving to the boot kernel to
So
do
you're
the
asking-
iSCSI booting.
Yeah. So how data can be passed from the boot kernel to
Yep, because,
the runtime kernel?
Because basically it would require probably defining several protocols or at least one in the UEFI spec, right?
Yeah. Yeah, I think currently, I think there's a few ways of passing information from the boot kernel to the runtime kernel. So for example, you could pass things as like Linux parameters. You could save stuff to the file system, load it back up. There's a Linux patch. It's not in upstream, but there's an open source Linux patch called PRAM, which lets you save a file system to memory, and then you can remount it in the runtime kernel. So there's a few different ways of transferring information from the boot kernel to the runtime kernel. I'm not too sure about the specifics of iSCSI, but one of those might work.
In the BIOS, will be moved to or used by the boot kernel, not by the runtime kernel per se. Because if we are actually trying to boot the runtime kernel from iSCSI, for example, like or PXE booting, right?
Yeah.
How the configuration from the BIOS will be passed to the boot kernel.
Yeah. So you would just write. In that case, I guess you'd implement iSCSI. I guess if there's a kernel driver, use that, or you could use something in user mode, and then you just pass like any information you need through to it.
Okay, great. That's it for questions. Please give a round of applause for Ryan already.